chapter 6, section 2 is about rotation. To talk about rotation, we need to remember flux, which was equal to AB cosine theta. We know that whenever we have a change in flux, we have induced EMF. How can we change flux? We can change flux by three different ways. First one is changing area. The second one is changing the magnetic field. And the last one is changing theta, which is about rotation. In this section, we will be changing the angle between the normal of the loop and the magnetic field. Simply you'll be rotating the loop, and this is actually the most practical way to produce and induce electricity. We have two systems that's explained in our book that produces electricity. The first one is called as hydroelectric power plant, and the second one is called as coal or natural gas power plant. We have more systems, but we are only talking about these two in our book. In the hydroelectric power plant, the falling water is directed against the blades of the turbine, and the turbine starts to rotate. The turbine is connected to a coil, so it will be rotating this coil inside a magnetic field. Now we have change in theta because of the rotation, so you'll have a change in flux continuously. You'll have induced EMF, induced current, and induced magnetic field. All of them happens together. In the coal or natural gas power plant, we are burning the coal or natural gas. It will produce a huge amount of heat, and the heat will convert water into steam. The steam will be directed toward the blades of the turbine, which is connected to the coil, which is rotating the coil too, and you'll have everything that we talked about it a moment ago. Let's talk about the Faraday's law that we had, which epsilon was equal to minus n engine flux divided by delta time, and flux is equal to AB cosine theta. Every delta that we see in physics is actually derivative, so we're taking the derivative of cosine theta. So we have minus n, AB are constant, they don't change in this case, which is rotation, and you'll have d cosine divided by d time. Theta here, we need to rewrite it as something else. To do that, we need to remember the equation that we talked about in chapter 1, which was saying omega is equal to delta theta over delta time. And when we generate electricity, we will keep the angular speed constant. Since angular speed omega is constant, every time will have its own theta. So we can get rid of the deltas. We can say that omega is equal to theta over time. When we rearrange this equation, theta will be equal to omega times time. So instead of theta, I will be writing it as omega times time. By the way, you don't need to know these derivations. They are all extra informations. It is fun to know where the equation of the generator comes from. So let's write the minus NAB again. They are constant. They don't change even if you take derivative, because the derivative is out of them. The derivative of cosine is minus sine omega t multiplied by omega. You have studied this in mathematics. Minus and minus will cancel each other, so you'll have n be a omega times sine omega t. And omega t, remember that it is equal to theta. We have another equation actually for omega, which omega is equal to delta theta over delta time. For a complete cycle, delta theta is 2 pi, and the time needed to complete one cycle is period. And 1 over period is equal to frequency, so we can rewrite omega as 2 pi times f. These are the equations that you need to know. You don't need the derivations. In the equation we have sine omega t, so epsilon is changing as a function of sine. So if we draw the graph of this induced EMF, we will get a sine wave, which we'll have later. So when we generate EMF, we will keep omega and the frequency constant. The maximum value will also be constant, but the one that is always changing will be the instantaneous values. Omega has some other names. First one that we have studied in chapter 1 was rotational speed and angular speed, but here we will also be calling it as angular frequency. And f is frequency, omega is angular frequency. So the maximum value that this can have will be equal to NBA omega, when sine theta has the maximum value. So we can rewrite the equation above as EMF is equal to Emax, which is NBA omega multiplied by sine theta or sine omega t. And that is actually the base of all equations that we have in section 3. Let's talk about an AC generator. An AC generator has 4 main parts. The first one is a permanent magnet to provide magnetic field. The second one is a coil. The third one, we have 2 slip rings. This is one of the main components that separates AC generator. And the last one, we have brushes. These are the permanent magnets. This is the coil. These are the slip rings, which are in contact. They are not attached, but they are in contact with brushes. When we have a coil that rotates in a magnetic field, the equation will be epsilon is equal to E max multiplied by sine theta, or sine omega t. Here I will be writing it as sine theta because I need theta here. Theta is between the normal of the loop or the area and the magnetic field. Let's have the picture here of all four cases. We have two orientations. On the left side, you can see that the loops are perpendicular to the magnetic field. On the right, the loops are parallel to the magnetic field. When the loop is perpendicular to the magnetic field, the angle between the normal and the field will be 0 because they are parallel to each other. The loop and the normal are opposite to each other. If the loop is perpendicular, the normal is parallel to the magnetic field. So in a question, it will always give you a loop that is parallel or perpendicular to the field. For theta, you need the angle between the normal and the field. Here, as you see, if they are parallel, theta will be equal to 0, sine 0 is equal to 0. Or in part C, you can see that the angle is 180 degrees, still it is parallel, so sine 180 is equal to 0. Since sine is equal to 0, epsilon max multiplied by 0 will be equal to 0. We will say that if the loop is perpendicular to the magnetic field, the induced EMF is equal to 0. We have two other explanations for this part. Let's check the velocities of each segment. If you pay attention to these velocities, velocity of segment A and velocity of segment C are parallel to the magnetic field. If the velocity of a wire of a charge is parallel to the magnetic field, the magnetic force will be equal to 0. Since magnetic force is equal to 0, induced EMF will also be equal to 0. And there is another explanation which is about the change in flux. At this orientation, the flux is maximum, but I don't need flux for induced EMF. I need change in flux. Change in flux at this orientation is equal to 0. And if change in flux is equal to 0, induced EMF will also be equal to 0. For the other orientation, when the loop is parallel to the magnetic field, the normal and the magnetic field will be perpendicular. We said that they are always opposite to each other. Since the loop is parallel, the normal is perpendicular. Since normal is perpendicular, the angle is 90 degrees and sine 90 is equal to 1. We will have maximum induced EMF. So we'll read it like this. We will say that if the loop is parallel to the magnetic field, the induced EMF is maximum. We can also explain it as the other two explanations like we did a moment ago. If we pay attention to the velocities of A and C, we will see that velocity of A is perpendicular to the magnetic field. Velocity of C is also perpendicular to the magnetic field. 94 is equal to maximum. In a coil, the maximum magnetic force must be parallel to the wire. This is a detail that we don't need a lot. Since the maximum magnetic force is available and it is parallel to the segment, induced EMF is equal to maximum. At this orientation, the flux is equal to 0, but that is just instantaneous flux, and I don't decide according to the instantaneous flux, but we decide according to the change in flux, and change in flux at this orientation is maximum. Since change in flux is maximum, induced EMF will also be maximum. Now let us draw the graph of all these four cases. We will be starting with point A. At point A, the loop is perpendicular to the magnetic field. The induced EMF is equal to 0 at this point because the loop is perpendicular. As it starts to rotate, the angle increases, magnetic force increases. As a result, induced EMF also increases until it reaches point B, which will reach its maximum or peak value. So the loop here is parallel to the magnetic field and induced EMF will be maximum. Please look at the galvanometer, which is reading plus maximum. On the graph, we will also have the maximum value. This is point B on the graph. The loop will continue to rotate. So theta at this time decreases, force decreases, EMF will decrease until it reaches point C, which will become 0 again because the loop here will be perpendicular to the magnetic field. Induced EMF will also be equal to 0. Pay attention to point C and point A. At point C, segment C is above and segment A is below, but at point A, segment A is above and segment C is below. So it is opposite to each other. As it continues to rotate, this time the induced one will be opposite to the point which we had a moment ago. As theta increases, force increases, EMF increases, but both will increase in the opposite direction. At point D, the EMF will reach its maximum value, but in the negative direction. And that's why the galvanometer is also reading minus maximum, because on the other side we have C, on this side we have A. But in point B, it was vice versa. A was on the other side, C is on this side. So the induced EMF here is minus maximum. And then it will continue to rotate. It will go back to point A, which goes back to 0. And that is one complete cycle, which shows that both EMF and current change as a sine function. According to the equation that we got from the generator, EMF was equal to E max times sine omega t or sine theta, and that proves the EMF and current will be changing as a sine function. In section 3, we will be using a potential difference instead of EMF. We will convert the epsilons to V, and V will be equal to V max times sine omega t, and I instantaneous will be equal to I max times sine omega t. We will be needing these two in section 3. We have another type of generator which is called as DC generator, and converting an AC generator into a DC generator is very easy. Simply convert these slip rings into split slip rings, which they have a name which is called as commutator. The commutators are actually slip rings. Let's pay attention to the AC generator. We have two slip rings. I will name them as slip ring 1, slip ring 2. I have two brushes. I will name it as brush A and brush B. Brush A and the first slip ring, they are always in contact, and brush B and slip ring 2, they are always in contact too. Whatever happens in the coil, you will have the same thing in the brushes. So if I have an AC in the coil, I will have the same AC in the brushes too. But if I pay attention to the DC generator, I have two split slip rings, two half slip rings. I will name it as the first commutator and the second commutator. And I have two brushes. I will name it as brush A and brush B. Here too, brush B is in contact with the first split slip ring commutator, and the second one is in contact with brush A. And let's say that in the coil I have a positive EMF or current that is produced inside the coil. Since they are in contact, I will have the same thing produced inside the brushes. So there's no problem until now. The problem starts, actually it is the solution, because we are trying to convert into a DC generator. As it rotates, the current in the coil will be reversed, because as it rotates, the split slip rings and the brushes are changing each other. So the first commutator will touch brush A this time, and the second commutator will touch brush B this time. So as you see, it has been reversed. So the commutator is reversing the reversed part. If you reverse something that's already reversed, so minus minus, you'll get it as positive. In the coil I will get an AC, but in the brushes I will get a pulsating DC. It is pulsating because it's changing magnitude. It is DC because it has a single direction. It is always positive or it is always negative. So it has a constant direction. So this is what we have in the brushes. And which one or which component is converting the AC into DC? The AC in the coil into DC in the brushes? That is done by the commutator. So we can say that a generator is a device that converts mechanical energy into electrical energy. So we get electrical energy at the end of the brushes and we can use it. What happens if we reverse the roles? So what happens if we give it electrical energy? Do we get mechanical energy at the end of it? Yes, we will get mechanical energy and you will have rotation. And such devices will be called as motor. Here we'll be focusing and studying on DC motor. DC motor has the same parts as and components as the DC generator. The most important one was the commutator. The rest is same. So we have magnets, we have coil, we have commutator, and at the end we have brushes. We can say that a motor is a device that converts electrical energy into mechanical energy. we need a source of electrical energy. How can we get a source of electrical energy? We can use a battery because we are talking about the DC motor, so we need to use a DC source. If we have a battery and if we connect a battery to a DC motor, it will apply a potential difference across the motor, and the potential difference will have its own current. So we will have a potential difference from the source. There will be a current that's coming from the source into the coil, and every current have its own magnetic field, which we have studied in section 2 of chapter 5. Now we have two magnetic fields that are in the same region with each other, the magnetic field of the coil and the magnetic field of the permanent magnet. So these two will repel each other and it will rotate the coil. But first, let's remember the compass. If you remember, when we insert a compass inside an external field, the compass will rotate until it has the same direction as the external magnetic field. When it has the same direction as the external magnetic field, it will stop and it will not rotate anymore. That's what exactly is happening to the coil too. So first the coil will be repelled by the permanent magnet, and the coil will be rotating so that the coil's magnetic field and the external magnetic field, which is the magnet's magnetic field, have the same direction. So when they have the same direction, the rotation stops. So they will repel each other until they have the same direction. At this exact moment, at this point, the commutator will be touching a different brush. So it is reversing the brushes. When it reverses the brushes, it will reverse the current in the coil. And if you reverse the direction of the current, then the direction of the magnetic field will also be reversed. We are back to the first point. We have reversed magnetic field, so they will repel each other again. The magnetic field of the coil and the magnetic field of the magnet will repel each other again, and this cycle continues, and we have a continuous rotation. So we always have a continuous reversing of the current, which will cause a continuous repulsion, which causes a continuous rotation. Let's look at the coil of the motor in the perspective of the generator. We have a coil that is rotating inside an external magnetic field. Whenever we have rotation of a coil inside the magnetic field, we have a change in theta, and since we have change in theta, we always will have a change in flux. We studied that whenever we have a change in flux, we have induced EMF. We have two EMFs, an EMF that is from the source, which is the battery, and another one that's induced because of the change in flux. Let's say that we have 15 volt from the battery and we have 5 volt that is induced. Since the induced is always opposing the change, so it will be in the opposite direction, and 15 volt is coming from the battery, 5 volt is induced produced in the opposite direction, it will have a net potential difference of 10 volt. The net potential difference has decreased, so we have less potential difference than the source. V net in the coil will be equal to the potential difference, or the EMF that comes from the source, minus the induced one. Since the induced is in the opposite direction, we will be calling this as back EMF. You can use the generator's equation, which was NBA omega. As the coil rotates faster, omega increases. As omega increases, back EMF also increases. As back EMF increases, the net potential difference in the coil decreases. According to Ohm's law, current is equal to V over R. The net current in the coil is equal to the potential difference across the coil divided by resistance. The resistance here is constant. As omega increases, back EMF increases, V in the coil decreases. As a result, the current in the coil also decreases. The back EMF tries to decrease the current in the coil. The last topic in section 2 is mutual induction. Mutual induction is the ability of a circuit to induce an EMF in a nearby circuit, but how? In the presence of a changing current. Let's have the picture. These two coils are not connected, okay? They are not connected electrically. They are insulated from each other. We have a primary coil, which is connected to the battery and a switch, and we have the secondary coil, which is connected to a galvanometer to see if there is an induced EMF or current in the secondary one. And there is an iron ring, which is used to enhance the change in flux. Let's have the current in the primary. One will be primary, two will be secondary. The magnetic field will be same for the primary and secondary, because if there is a magnetic field in the primary coil, the iron ring will also be magnetized. As a result, we will have the same magnetic field in the secondary coil. We will have a flux in the secondary coil. We will see if there is a change in flux in the secondary coil. We will see if there is an induced EMF in the secondary coil. First, when the switch is always open, the current in the primary is zero, so the magnetic field in both coils will be equal to zero, and flux in the secondary coil will also be equal to zero. The change in flux is zero because there is nothing and there is no change, and induced EMF in the secondary coil will also be equal to zero. But when we close the switch, the moment of closing the switch, the current in the primary coil increases and goes to maximum right away, so there will be a change in the magnetic field. As a result, there will be a change in the flux in the secondary coil, which goes from zero to maximum, so the change is plus maximum. Since there's a change in the secondary coil in flux, there will be an induced EMF, and the induced EMF will oppose the change. As a magnitude, it will be maximum, but as a direction, it will be opposing the change. Since the change is positive, increasing, this will be negative. As the switch stays closed, everything will remain maximum. By everything, I mean the current in the primary, the magnetic field in both coils will be staying maximum, and the flux in the secondary coil will also stay maximum. So there is no change in the flux. It was maximum, now still it is maximum. It is always maximum, so there is no change. The change is equal to zero. If there is no change, there is no induced EMF. So induced EMF in the secondary coil will be equal to zero if the switch stays closed. So at the moment of opening, we will see that as we open it, the current goes to zero, the magnetic field goes to zero, the flux also goes to zero, and we see that the flux has gone from maximum to zero, so the change in flux is minus maximum. Since we have a change in flux, we will have induced EMF, but since the change is minus, the induced will be positive. If we pay attention to the needle of the galvanometer, we will see that if at the moment of closing the needle was moving to the right side, in the moment of closing the needle will go to the left, and that is because the change is opposite or reversed, so the induced EMF will also be reversed. So we can clearly say that whenever we have a change in the current in the primary coil, there will be a change in the flux that happens in the secondary coil. Since we have a change in the flux in the secondary coil, we will have an induced EMF in the secondary coil, and we can write the equation as E2 is equal to minus M, change in the current 1 divided by delta time. Remember that the change in the current happens in the primary, and the induced EMF is produced or induced in the secondary coil, and M is called as coefficient of mutual induction, or simply mutual inductance. We can say that the unit is Henry. Why the unit is Henry? There is an equation, a relation which we don't need it, and it is extra, and you don't need it, it is not included. M is equal to the square root of L1 times L2. L1 is the coefficient of self-induction of the primary, L2 is the coefficient of self-induction of the secondary coil. Each one has a unit of Henry times Henry in a square root. The result will be Henry, and each L is equal to mu n square area over L, or 2R. L is for the solenoid and 2R is for a coil. We can say that mutual inductance depends on two properties. The first one is the geometrical properties of the coils, like we have in the equation of the L, number of loops, area, L, and the radius, and so on. And we can also say that the number of loops is the most important one, which we'll be studying it in section 3. The second point that inductance depends on is the coil orientations according to each other. If the coils are parallel with respect to each other, the mutual inductance will be maximum, and if the coils are perpendicular to each other, mutual inductance will be minimum. Remember that mutual induction is the base of a very useful device which is called as transformer, which will be studied in section